Hello students, welcome you all. In spectroscopy, today I will discuss one of the interesting topic is color and conjugation. So if you have seen in your daily life, then some of the substance like tomato, which is colored, that is red in color, like carrot, sometimes orange or this red in color, blood, which is red in color, leaves generally green in color. So why these substances are colored? So we can answer this question with the help of chemistry or with the help of this UV visible spectroscopy. Now, so this tomato, if you have seen, this tomato, this is red in color, and then carrot, orange or red in color, and then if you have seen this blood, which is red in color, and the leaves, which is green in color, and egg yolk, if you have seen egg yolk, then this is yellow in color. So why these substances are colored? So whereas if you have seen the natural rubber, if you have seen the natural rubber, then this is a milky white in color. So why the rubber is not colored, whereas why this is colored? So one of this answer that these substance contain one of the pigment which is red in color, and also they contain the conjugated pi bonds. So one of the reason that they contain many conjugated pi bonds. They contain many conjugated pi bonds. Okay, so if conjugated pi bonds are there, then delocalization of electron will take place. If delocalization means it is a stable one and it will absorb energy, which is very less energy. It will absorb less energy. Okay, so they contain many conjugated pi bonds. So what I told, this tomato contains one of the pigment which is called as the lycopene. And due to this pigment, it appears red in color, whereas this contains beta-carotene as a pigment. And this blood, all of you know, this heme is one of the pigment which is contained. Leaves, it contains chlorophyll as a pigment, and this egg yolk, it contains lutein as a pigment, due to which this appears yellow in color. Okay, so these substances, they absorb some light, and after absorbing the light and complementary color that appears, so they absorb one of the electromagnetic radiation which falls in the visible region. Okay, and visible region, it means if any substance absorb visible light, then they appear colored. So they absorb visible light, they absorb visible electromagnetic radiation, and they absorb high wavelength and visible light. If I will discuss in a UV visible spectroscopy, so the UV radiation, it falls, the range for this UV is around 200 to 400 nanometer, whereas this visible, they falls under the range 400 to 800 nanometer. Okay, so they absorb a visible light which is under the range 400 to 800 nanometer, and that's why they appear colored. So as the wavelength increases, it means energy decreases, or if we can say, they absorb. So UV light has high energy, low wavelength. Visible light has low energy and high wavelength. So these substances, they absorb low energy radiation. So why they absorb low energy radiation, or we will understand more when we will study the UV visible spectroscopy. So in this case, here in these molecules, the energy gap after when any light is absorbed, then the electron, or when UV visible light is absorbed, electron go from lower energy state to the higher energy state, or electron go from lower electronic state, ground electronic state, to the excited electronic state. Or we can say electron go from lowest occupied molecular orbital, highest occupied molecular orbital to the lowest unoccupied molecular orbital, that is from LUMO to HOMO. And in these cases, the energy gap between HOMO and LUMO is very less. So in these cases, the energy gap between HOMO and LUMO, this energy gap is very less in these molecules. So why they are colored? Because energy is less and wavelength is high. So because energy, why they are colored? Because the energy gap between HOMO and LUMO is very less. So as the number of conjugated pi bond increases, energy gap between HOMO and LUMO start decreasing. If one more conjugated pi bond, it decreases more. If one more conjugated pi bond, it decreases more. So like this. So as the conjugation increases, energy gap between this and this will decrease. So that's why if energy gap decrease, then it will absorb, it means that it will absorb higher wavelength of light, which falls under the visible region of electromagnetic spectrum. So this is the reason. So on the other side, if we see the natural rubber, if you have seen, then this natural rubber is milky white in color. Milky white. So why it is milky white? So it is not colored. So why it is milky white? Because it contains no conjugated pi bond. Because it contains no, or we can say no conjugated pi bonds. Conjugated pi bonds are not present over here. So conjugated pi bonds are not present in these. So this is a natural rubber. It is made up of a isoprene unit. When lot of isoprene unit combine, then we get a natural rubber. And if you have seen this isoprene, which is this is our isoprene, that is 2-methyl-1,3-butadiene. When lot of this isoprene unit combine, then we get this polyisoprene, which is called as the natural rubber. And if you have seen this structure, then the structure is so like this. So this is our natural rubber, and as you can see, there are many pi bonds. Many pi bonds are present, but they are not conjugated. So that's why it is milky white in color. Whereas if you will see the lycopene, then lycopene, it contains 11 conjugated bonds. So lycopene, if you will see the structure for this lycopene, then it has 11 conjugated pi bonds. Okay, it has 11 conjugated pi bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 conjugated pi bonds are present in lycopene. So these are the 11 conjugated pi bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whereas this is the isolated pi bond, and these two are the isolated pi bond. They are not the conjugated one. These are the isolated pi bond. Isolated pi bond, and this is also the isolated pi bond. Okay, so it has 11 conjugated pi bonds, and its formula is C40H58. C40H58. Okay, so now, so in the same way, this, if you will see the beta carotene, then beta carotene also contains the 11 conjugated pi bond. So if I draw the structure of this beta carotene, then beta carotene, it has the structure okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and okay, this is 10 and this is 11. So it has 11 conjugated pi bond in beta carotene. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 conjugated bonds, 11 conjugated pi bonds, they are present in beta carotene. So this is the structure of beta carotene. So due to this, this is colored in nature. So this is colored in nature, beta carotene. Okay, now so sometimes what you have seen, what we have seen in that sometimes this tomato or sauce which contains the tomato, it falls over our cloths, and they cannot be removed even by the washing. So what is the reason that they cannot be removed? Or otherwise, because it contains the pi bond, and until and unless these pi bonds are removed, it means until and unless this unsaturation is removed, then only the color of this tomato, that is red color, and that can be washed out. So if this is not become saturated, then the color will not be removed. So it can only be removed if we wash it containing any bleach. So bleach removes the color. Bleach can remove the color easily, or otherwise it wash out. After many wash, the color of this sauce disappears from our cloth. So if we want to disappear the color, then we should use a good bleach, or some good bleaching agent is used. Or otherwise, what we can see, suppose if we want to saturate it, so 11 unsaturated pi bonds are there, unsaturation is there, and suppose if we treat this lycopene with palladium charcoal, if we do the hydrogenation in presence of palladium charcoal, then this lycopene, it becomes lycopene. It becomes the lycopene, and having the molecular formula C40H82. So as you can see, in lycopene, all the double bonds are removed, or we can say all the double bonds are get saturated. So whole molecule, this lycopene gets saturated to get the lycopene. Okay, so in the same theory can be used to wash the color from our cloth. So if we use a good bleach, then we can wash the color, we can wash the, or we can remove the double bond from, we can remove the double bond of the color. So usually the bleaching, good bleaching agent like Cl2 in presence of H2, that can be used as a bleaching agent, or we can use the sodium hypochlorite in presence of H2O. So this can be used as a bleaching agent. So suppose if we have a double bond, and if we treat it with sodium hypochlorite in H2O, then what will happen? This will add across this double bond, and double bond it will get removed, and in this way the bleach works. So bleach works by removing the color. So bleach works by removing the color, and here we can see this get OH and this Cl. This OH and Cl is added across the double bond, and in this way the bleach works. So this is about the color and conjugation in some of the molecules, in some of the substances which are we are using in a daily life. So we will study more about the some conjugated molecules in UV visible spectroscopy later on. Okay, thank you.